Hello everyone, welcome to my video. Following linear impulse and linear momentum, in this video we will explore angular impulse and momentum. By now, we already know that linear momentum g equals to mv, where g and v are vectors. Let's add a random point of interest O here. Connecting from O to the particle, we can obtain the position vector r that describes the location of the particle with respect to O. Then we'll define the vector cross product of r and mv as angular momentum, give it new name h0 or ho. Since it is a vector cross product, we can use the right-hand rule to determine the direction. In this case, ho is coming out from and perpendicular to the screen, or should be pointing towards you if you use your right-hand rule. If the direction of ho was not clear on the previous page, let's tilt it a little bit. Now I tilted the page. Here we can see now ho as a cross product is coming out of vector r and mv and perpendicular to them, to both. We can also take a look of this concept in 2D. If you still remember, the cross product can be written as rmv sine theta, and this is the magnitude of angular momentum. Since we started with this vector form, as long as we can find the vector, this vector can be either in 2D or 3D. In 3D, we will still do the cross product and obtain the angular momentum of each axis. Okay, now we know this can be applied to either 2D and 3D. Lastly, the unit. The unit of angular momentum is kilogram meter per second meter in SI unit, or pound feet second in imperial unit. Recall from your statics course, moment m can be calculated by F times d, the perpendicular distance from F to the point of interest O. Moment can be calculated either using scalar or vector form. I hope you still remember. The reason I'm bringing it up here is because I want you to think about one question, or three questions. Looking at the wrench on the right side, why counterclockwise rotation will unfasten the nut, and why clockwise wrench rotation will fasten the nut, and why we usually define counterclockwise as positive direction anyway. Okay, I'll leave these three questions to you. Let's continue with the vector format of the moment. If there are multiple forces, the overall moment about O, the point of interest, can be calculated in two ways. You can add all forces together to find the resultant force, then find the ultimate moment of the resultant force about O. Or the other way to think about this, you can find the moment of each force about O and then add the moment together. Either way, you will end up with a total moment about O is sum of MO equals to R cross product sum of F. This can be explained in word as all forces acting on an object creates an overall moment about O, the point of interest. Carrying this forward, we can once again involve F equal to ma, our best friend now, to replace the F part in the equation. And then we end up with sum of MO equals to R cross product MV dot, or MA. At the beginning of this video, we defined angular momentum as HO, or H0, equals to R cross product MV. And we can divide dt on both sides and manipulate the equation a bit, and we'll arrive at HO naught, the derivative of HO, equals to V cross MV plus R cross MV dot. The good thing happens here. We see that there is a V cross V, which is 0. Right? Cross product of the vector itself is 0. Therefore, the angular momentum H0 dot can be written as equals to R cross product MV dot, which is also equal to the left-hand side, sum of MO. Therefore, we have sum of MO equals to HO naught. This means the moment MO of a point O of the resultant force equals to the time rate of change of angular momentum HO naught of point O. Let me help you clarify a little bit. The moment MO is created by a force, whereas the angular momentum is generated due to the velocity and mass, mv. Okay, distinguish these two very clearly. Same as all other variables, sum of MO and HO naught can be analyzed or broken into different directions, x, y, z, as needed. Now, we can proceed with taking the integral of this equation. As I said, lots of calculus here. Then we can get the change in angular momentum can be calculated between time t1 and t2. This equation is called the angular impulse and momentum principle. And in this equation, the sum of MO times dt part is what we call the angular impulse, the moment times time. Compared to the linear impulse F times t, this is actually very similar, and we will compare them side by side on the next slide. Quick recall on our linear momentum and impulse. We have linear impulse F times t, linear momentum mv equals to g, and the angular impulse momentum principle and the conservation of linear momentum. As for angular perspective, we have angular impulse mo times t, and there is one more step to get mo by taking the cross product of r and f. Then we have angular momentum and angular impulse momentum principle written here. You can see how similar are they between linear and angular. Lastly, we have the conservation law. We call it the conservation of angular momentum. Now, if you take a look at this side by side between linear and angular, mathematically speaking, the angular side just has one more variable to deal with, which is the position vector r. We will look at the conservation of angular momentum here. Most of the time, we're going to work with the 2D motion. The conservation of angular momentum happens when there is no external forces or external transverse forces acting on the line of movement. In other words, hopefully you can understand this better, you have force that is acting on the object perpendicular to the path that is not going to change the angular momentum. Using our knowledge from the tangential normal coordinate system, this means any normal force won't break the conservation of angular momentum. Only when there is a tangential force exist, the angular momentum is no longer conserved. Okay, there are two directions. One is going with the direction of traveling. One is perpendicular. The perpendicular one won't impact the conservation of angular momentum. Finally, looking at this angular impulse and momentum principle equation, it tells us from point 1 to 2, when there is a force acted on the particle during the movement, the angular momentum will change from HO1 to HO2. Another way to say this is angular impulse causes the change in angular momentum. Because momentum is conserved usually, but when there is angular impulse applied, the momentum will change. Here's a list of recommended readings. Thanks for watching. I'll see you next time.